This is the GCSE physics presentation looking at the motor effect. To get started, you've got three different arrangements of magnets. Treat them in sets of twos, and all you have to do is sketch what the magnetic field lines would look like between those pairs of magnets. Pause the presentation now, and when you're ready, you can restart and have a look at your answers. So these are the diagrams you should have drawn. In the first of the sets of magnets, you've got a north pole next to a south pole, so the magnetic field lines will go from north to south. In the other two sets of arrangements, the magnets are paired off so that like poles are facing each other. So we have two north poles facing each other and then two south poles facing each other. As a consequence, you can see the magnetic field lines bend away from each other. In this lesson, we're going to look at a principle called the motor effect, and we're going to look at how we can increase the force involved in the motor effect. Well, if we have a wire with an electrical current flowing through it, that wire will have its own magnetic field. There's also a magnetic field, as we've just seen, that exists going from the north pole of one magnet to the south pole of another magnet. If we place a wire with the current flowing through it into the magnetic field between the north and south pole of the two magnets, we end up with two magnetic fields that will combine together, and as a consequence, the wire and the magnets will exert a force upon each other. When a wire with the current flowing through it, and that the current has to be flowing, there has to be an electrical current through the wire, or this does not happen. But if we have a wire with a current flowing through it, it'll experience a force in a magnetic field, and this is what we refer to when we talk about the motor effect. There are a couple of criteria for the motor effect to occur. Firstly, as we've already said, we need to have a current flowing through the wire, but we also have to have the angle of the wire at 90 degrees to the direction that the field lines are traveling in from the magnets. If the magnetic field lines and the direction of flow of current are parallel with each other, we will have zero force. If we have the magnetic field lines and the direction that the current traveling in at 90 degrees to each other, then we will have the maximum amount of force, or 100% of the force that could have been generated with those particular magnets and that particular current. If we change the angle between completely parallel and 90 degrees or perpendicular, we can change the amount of force. As we get closer to perpendicular or 90 degrees, we increase the force up until the maximum. As we move more towards a parallel arrangement, then we are reducing the force and we're getting closer to zero when they're parallel. We have a concept called magnetic flux density, and it's a way of measuring the strength of a magnetic field. We use the units of Teslas, and what we can do is we can actually use magnetic flux density to measure the force that's exerted on a wire when that wire has a current flowing through it inside a magnetic field. In GCSE physics for AQA, you're actually given that equation as one of the 12 equations in the exam, so you don't have to memorize it, but you do of course need to know what the variables are, and you do need to be able to use it. It's important to note that the calculation can only be used when the current is traveling at right angles to a magnetic field. It's the only time this equation applies, and it may be that in the exam they ask you under what conditions can this particular equation be applied, or what do we have to assume when we use this equation, and it's the fact that the current is at right angles to the magnetic field. So to calculate the force involved in a wire in the motor effect, we've got magnetic flux density, and we have to times that by the current traveling through the wire measured in amps, and of course the length of the wire that's inside the magnetic field also applies. Quite often in the exam they will give you the magnetic flux density, the current, and the length, and ask you to calculate the force Or if it's a larger mark question, what they may ask you to do is somehow give you some variables to work out the current and then calculate the force involved using magnetic flux density, your calculation for current and the length of the wire, and possibly even measure the length of a wire, take the length of a wire from a diagram. Now there's several ways that the force exerted can be increased. Pause the presentation, have a think, look at the equipment. How could we increase the force between the magnets and the wire? Pause now, restart when you're ready. Well, to increase the force, there's two ways we can do that. We can increase the strength of the magnetic field, or we can increase the current that's flowing through the wire. The last thing we're going to look at is what's called Fleming's left-hand rule. And Fleming's left-hand rule is applied to the motor effect and it lets you work out the direction the wire would move in if it was in the magnet. And you need to be able to make the shape as seen in the picture on the right-hand side using the thumb and first two fingers on your hand. Remember, it's your left hand. There is a different rule for your right hand, and that's covered in a different presentation. When we're looking at your left hand, you can change the wording, but as long as you know which finger or thumb represents which part of the motor effect, it's not necessary for you to learn it in this way, but this is the conventional way of learning it. Thumb has the M in it for motion, and that's the direction the wire would move in. The first finger has an F, which is for field, which is the direction of the magnetic field, and the second finger has the C for second and has a C for current. If you can come up with a better system, by all means come up with a better system, but this is a traditional one. And what we do is we use our two fingers and thumb, we create that shape, and always start by creating the shape. If you create the shape and then line stuff up, it's so much easier than trying to do it finger, and thumb. You end up getting in a bit of a muddle. If we look at our original diagram and we now get our left hand and make our left hand rule shape, what we should be able to do is identify if the wire would move up or if the wire would move down. So I'd like you to pause the presentation, make the shape, then match it up to the different variables, and then see if you can come up with what direction the wire would move in. Pause the presentation now, have a go, and restart when you're ready to check your answers. Well, if you line up, you should find that your first finger, which is the field finger, should be going from left to right, literally in front of the screen. When you do that, if you do that with just the finger on its own, it's not going to cause problems. The problems you're going to find in this next bit is that the current is actually traveling into the screen. It's traveling up along the green line away from your face. Now, if you haven't made the shape, you're now trying to put your hands and fingers into all sorts of weird and wonderful shapes to try and get this to fit. If you make the shape that you should start with your thumb straight up, your finger pointing to the right, and your second finger pointing towards you, and then simply rotate your wrist. One way will be extremely uncomfortable and you can't do it, and the other way will be a bit more comfortable, and you should be able to get your second finger pointing towards the screen. And when you do that, you will notice that your thumb is pointing down. And that means in this particular arrangement, the thumb represents the movement of the wire, so that green wire would move down. Just to finish off, last thing I'd like you to do is come up with 3 things you knew before you started the lesson. So 3 of the things that we've covered that you already knew, 2 things that you've learned this lesson, and 1 thing you're not sure about, or 1 thing you need to go back and check, or 1 thing for yourself to check in a couple of days' time whenever you're looking back over this material.